Hello, my name is Gabriel, and welcome to a new episode from Concierge. In our last episode, we have created the first proof of concept page for LLM interaction, where we were feeding a customer name and the whole list of information from our database, and the LLM was presenting all the information about that customer. In this episode, we want to implement the testing methodology so that we can start playing with this prompt, see the impact, and start playing with other LLMs and see what we need to do in order to achieve satisfactory performance. So our first prompt from today will be to create a performance testing folder in which there should be an endpoint of some sorts, which will take customer name. We will always use the same customer name in order to have exact results, and should measure how long it takes for the response to come. This test should be performed multiple times. Probably we want to run it 5 times in a row, and then we would like to run it 8 times in parallel. By running 5 times in a row, we want to see what happens when we bring optimizations to caching, and by running 8 times in parallel, we want to see what happens when the way that the model works changes. We want to log this information in a table. Probably it will be better to use a new database for this instead of the hotel one. And we also want to log the model name. This will allow us to have a decent table at the end based on which we can assess the performance of different models. And as new models get pushed, or we discover new ones, or the versions of vllm evolve, we can rerun the tests and have a delta between the older version and the newer version. So the prompt goes as follows: create a new performance test folder. In this folder, there should be a Python file which calls our current implementation, query guess for LLM, using the name that we already chose for test. There should be 2 types of tests. One should send 5 requests back to back, and the second should send 8 simultaneous requests. There should be a new SQLite database called performance test. In this database, we should log the model name, context length, the LLM version, system prompt, user prompt, if the requested response format was JSON or text. In case of JSON, we should log if it was a malformed format. For each request, we should log the time when it was sent and the time when the answer was received. We should not force any timeout because we already know that some of them will be very long and some will never finish. And we also added the endpoint the test suite can use to retrieve information about the currently loaded model. Let's see the plan. It looks good overall. Since this is a tool, it is expected to be improved. I already know for sure that it is not everything that we want, because we do not log if it is a thinking or a non-thinking model. There's no need to bother with milliseconds and microseconds, so on and so forth. No LLM will be able to answer that fast. We are talking about some seconds in the best case scenario. So we are ready to start the implementation. We have also improved the usability a little bit. We have tried to create a web page around the run performance test script file. Like this, it is easier to set the values which are not visible in a V1 model's endpoint. And there is another problem that has to be solved before running this. Inside run performance test, the system prompt and the user prompt are copied from llm.py. This is wrong because as we will play with prompt in llm.py, we should reuse the same thing in the test. So the 2 of them should be exported somewhere in a file or in a setting somewhere and be reused in both places. Also during testing, I think we will observe that the delta between the fastest and the slowest answer for the same LLM is quite big. And I think 5 consecutive tests is not enough. I think we'll need maybe 10 or 15. Reason being that the outcome is almost never the same and the generation speed will be different. From processing will be similar or equal because we always send the same prompt, but the generation is totally random. In the future, we should also include how much cache hit was in vllm, because this will change, usually increase more and more the more we send the same prompt. So it is totally normal that the last one, if it has the same number of tokens as the first one, will be fast. The result of this will be very ugly and very messy, because right now in the user prompt we have all the other database. And if we decide to test what happens when we send the database as a prompt, then we'll have the same problem in the system prompt. The good thing is that our database is static. We seed it from the same information all the time. So maybe down the line, we can store just the length of the system prompt and the length of the user prompt. Let's refresh the information, set the correct values, run it for the first time to see what happens. Indeed, this may take a while. It is a bit strange that we don't see when requests are going. I would prefer some sort of output where it says sending first, sending second, etc. Another thing that we need to add, even at this stage, is to have a normal query which counts how many times this guest actually exists in the database, because with this information we need to validate how many times it is returned or retrieved by the LLM. If the LLM answers with one occurrence, but we know there should be 4, that has to be considered as a failure. It is not something that can function in a production environment. So in case of a JSON object, there should be a list of objects, and the number of objects should be then equal with the number of entries in the database. And in case of free form, as it is here, maybe have at least a regex which validates that this string can be found a number of times. Even that is error prone, because one LLM can retrieve information about reservations, rooms, like all the objects, and another one can retrieve only customer name. And if we do a regex search just by the number of occurrences, we will get 4. But in reality, the difference is super big. So this testing methodology should be developed more before we are happy with the end results. What we are trying to log, if there is any difference between sending the prompt as a system prompt or as a user prompt. The reason why we are doing this is because in all the backend there are 2 steps when it comes to LLMs or prompt. There is the part with prompt processing, which happens first, and in that part the information received is transformed from pure text into something called key value representation, let's say. That part is cached if it never changes. So by sending our database in the system prompt, we will always make sure that we hit that level of cache. That is important when we have subsequent queries. The advantage when sending it as we are sending now in the user prompt is that it is more dynamic. When we choose to send it as a system prompt, you can imagine some layers. We define at backend level, in my case in vllm, how many tokens is considered to be one unit of cache. The more tokens, the bigger the buckets of cache are, and the faster they will be read. The smaller number, the more buckets of cache we have, but they are slower to be read. The advantage in this case, if we will send the whole database all the time, if we structure the information with the information that changes the least on top and then the information that changes the most at the bottom, that when it goes through prompt processing and it builds the KV cache, it will invalidate only as soon as it finds a change. So a part of it might always remain cache and not be recalculated. If we look here in the terminal, there was a difference of 40 seconds between first and second request. This is very likely due to this cache. We'll see if the third request has something similar with 151. It is not necessarily the case, because with the configuration that I have now, I think vllm accepts only one connection and a bit, so it will return very bad results. But let's see. I expect the third one to be in this range. At some point there can be thermal throttling and we can go above this. Okay, the third result came in and it was slightly better than this. We don't really know right now the exact length of the answer, but I expect it to be the caching that improved things a little bit. We'll see when we show the information. How we can go about validating the answer in the text-based approach would be to use a discriminator. So we let the tests run, then we load a smart model and we feed the answers to this model and we ask it if it contains the correct information. And by correct information, we look at the database, we look at what are all the possible fields, and we ask it if it contains, in our case, 4 blocks of these fields. And with this, based on its answer, we calculate some sort of deviation. For our 5 sequential tests and 8 concurrent tests, it can be done manually, but later down the line, if we will have more, it starts to get a little bit complex. It is good to see that request number 2, 3, and 4 have a very similar time. This means that we can assume that as soon as the KV cache is being built on the first request, the others will be significantly faster. In our case, 40 seconds, it is significant. How we can use this information is to refresh the cache as soon as there is an update in the database or a relevant update. Another way we can think about these problems is to look at NoSQL database. The type of improvements that are being done there can be reused here. It is very true that we can use such a database altogether and avoid all the LLM part. But now the LLM for us is just a silly example to see that things work and to play a little bit. It is not the end goal. The end goal is to provide our final user with a way of writing prompts and improving its prompt in order to create pages with blocks, and each block it is its own prompt, so that the user can totally configure the way that this application looks like based on the information that it has. Now we are starting to test concurrent requests. What is interesting here is to add up the total duration of the sequential. So we can consider a baseline of 151.85 maybe. We can multiply this by 8 and see if the total length of the concurrent requests is smaller than this. Okay, I think everything has concluded successfully. I wonder if these have finished at the same time, because if yes, it is a very big improvement over if we consider 151.9 multiplied by 8 would be 1215, and if this actually finished in 236, here we have to check the timestamps between the lowest beginning and highest end, because they start in the same time, but they shift a little bit as soon as they reach the end point in the same time, but then they shift a little bit and then they go in parallel, and at some point all of them finish, but there is a little gap. So when we add all together, we don't literally have to add all these. It's not how it works. Let us see. Okay, so labs length 1. We didn't log the length. I'm kind of bad. Do we have the length send and database? If not, these are the kind of bugs that we should fix before. So now here, the response and time exists. Database is good, so it doesn't exist in, or it's a little bit of a list form. So let's debug this, let's make it work, and then we can analyze again if concurrent and sequential were actually running at the same speed. Good. A few fixes later. So current conclusion is that for concurrent users, it actually took 4 minutes, more or less. Some were faster, but 4 minutes. And for sequential, it took 3 minutes per request. So concurrent, it will scale much faster than sequential in this use case, even if GPU is at full load all the time. This is an interesting finding, but this is the case because the KV cache remains the same. If we change, what we should test next is what happens if the first bit of the user prompt changes for every request. That will invalidate the cache, and I expect it to be different. Now, what we also need here in this table is some sort of a button to see the response action, because there is a big discrepancy here. It was 1400 characters, and here it was 1500. So we need to see at least manually what's the difference. For sure, these with 1581 are the same. And the reason why vllm could achieve such a speed for 8 concurrent users was because of caching. It calculated first one and then the others contain the same information. So this is the end of this episode. Now, before optimizing for other models and optimize the prompt, we need to improve a little bit the output. We need to be able to validate what is inside the results, and we need to maybe think of a way how to store this information. So right now we are using a performance database, but this will grow out of scope super fast. If we run it one more time, we will already have a scroll bar, and we will have to select or display just some of them. We should add a new column for each test run, store when it was run, or give it a friendly name. Like this, we can query just for some of them. We'll choose one of the options in the next episode. We're already very good on track with what. Thank you very much for watching. See you in the next one.